Yeah, give me one sec.
The future is watching. Welcome to Opcode Virtual Summit.
Start video. Can you see me? Okay, let me just, I can stop it. Okay, I'm ready. Let me just retweet to say I'm live. Okay, awesome. You can see my screen okay and see me as well?
Yeah, we should see your screen now. Let me just share it to you. And yeah, you are live now.
All right, good evening or good morning, depending, I guess, where you're at in the world. I first want to thank Matt for inviting me to speak yet again. Definitely stoked to be talking nerdy about some really interesting Mac malware that I analyzed. So today we're going to be kind of walking through the comprehensive analysis of this malware. So we're going to talk about first its infection vector, how it got onto end users' Mac systems. We're going to talk then about how it persisted, how it installed itself so that every time the system was rebooted, it would be re-executed. And then the next part, we're going to kind of dive into some of its capabilities and show some very interesting features that this malware had that we really haven't seen in other malware specimens recently. So I'm going to dive in. If you want to follow along, I'm basically going to be walking through my blog post on the topic. It's got all the graphics and screenshots, so I figured that was kind of the easiest way to do. So feel free to also, hop on the website if you want to see that as well. The other thing is I've shared the sample of the binary of the malware itself. So if you want to, perhaps after this talk, take a closer look, you can actually download the sample, run it, in a VM. Make sure you don't infect it yourself. It is live actual malware. So then you might be able to apply some of the things we talked about today. If you're more interested in, maybe trying to follow along or kind of play around with it some more, because there's still some open questions regarding the malware. So how did we come across this malware? Well, a malware researcher named Dinesh tweeted about it. I believe he found it on VirusTotal. At the time, it was there were 0 detections, which is not too surprising for a variety of reasons. First and foremost, the engines on VirusTotal are often just the product's signature-based scanners. So a lot of security products have more comprehensive detection capabilities. They may, for example, look for certain behaviors. But on VirusTotal, it's generally just the signature-based ones. So any new malware is obviously not going to have a signature for it. So generally, that's undetected. So Dinesh was kind enough to tag me in his tweet. I was intrigued, as he mentioned initially, it looked like this was a piece of ransomware. We don't see a lot of ransomware targeting macOS. And I also had created in the past some products to generically detect ransomware. So I thought this was an interesting sample to dig into and also test to see if my tool was able to detect its ransomware capabilities. So next question, how does this malware get onto end users' systems? So in Dinesh's tweet, he didn't mention anything about it. However, Thomas Reed, who works at Malwarebytes, was doing some analysis and research on the malware as well. And he noted that it was spreading via pirated versions of popular macOS software on torrent sites, specifically in Russia. Now, this isn't a very sophisticated infection mechanism, but it's pretty common. So in the past, we've seen other malware abuse this technique. The idea is basically pirates or hackers, or crackers more technically, will take a popular application, something like Photoshop or perhaps Microsoft Office, something that is expensive and in demand. What they'll do is they'll often crack the application, bypass its copy protections so that users can use it for free, right, without a license, or perhaps they'll package it with a key generation application. but a lot of times they'll also inject some malicious code. So basically trojanizing the application. So as I mentioned, there's other malware that we've seen utilize this technique. iWorm was one. It was spread via Trojan applications on Pirate Bay. You can see on the slide, for example, things like Photoshop, Microsoft Office. This was from a few years ago. Well, actually now almost 10 years ago. So common technique. Obviously, users who downloaded and executed these pirated applications would be infected. So iWorm was one example. Another one was Schlayer. Again, we can see in the quote via BitTorrent file sharing sites, it infected was a fake Flash player update. So that was kind of interesting as well. So a takeaway kind of from this is, ethical reasons aside, is definitely be careful when if you are running or installing pirated software, because it's often infected with malware. And there's a great quote that kind of captures this. And, it basically says, these torrent sites often are kind of breeding grounds for malicious code as well. So, if you're a user, again, ethical reasons aside, definitely be cautious installing the pirated applications, because in this case, if you would have downloaded one of the pirated applications that EvilQuest had injected itself into, you would become infected. So the specific instance or sample we're going to be analyzing, talking about today, was in a pirated version of the popular DJ software called Mixed-In-Key. And again, this was available for download via these Russian torrent sites. First thing we can notice is the package is unsigned. I use a utility I wrote called What's Your Sign. Basically allows you to write or control click on any file, and then it'll very quickly tell you its code signing information via the UI. Since the package is unsigned, when you go to open it on recent versions of macOS, there will be a prompt from the operating system. Basically, the operating system says, hey, can't verify this, make sure or be extra careful opening this because it might contain malware. Now, if you see this pop up, doesn't necessarily mean the application has malware, but maybe again be extra cautious. However, it's likely that Mac users who are downloading pirated software are not going to be stopped or worried by this prompt, so they're probably going to click OK, pressing onwards, which will unfortunately mean that they would then be infected via EvilQuest. So let's now kind of dive in a little deeper and start actually analyzing the package, the scripts, and the binaries to see how this malware operates. So we already mentioned it's distributed via Trojanized installers. We're going to be focusing on a disk image named mixedinkey.dmg. Again, this is a Trojanized pirated version of the Mixed-In-Key DJ software. It's kind of interesting to see them targeting users of, perhaps DJs. But again, this is just likely a popular software package that a lot of people are searching for on these torrent sites. When I did this analysis, the disk image was not flagged by any of the antivirus engines on VirusTotal. I mentioned this is not too surprising. New malware generally doesn't have signatures. The engines on VirusTotals are generally purely signature-based, so really unsurprising. I believe now, though, there are signatures for this based on the fact that this malware has now been analyzed, and the AV engines have had some time to generate and test signatures for this. So the first thing I do is when I get a disk image, I mount it. And there's a few ways to do this. I use the command line, specifically the HDI util command. We execute that with the attach argument and then the path to the DMG. And this will just mount it. This will attach it onto the file system so that we can view the files within that. Obviously, we're looking to extract the content from the disk image, that DMG file, so that we can continue our analysis. So if we do that, we can see it's mounted to dev disk S3, specifically to /volumes mixed-in-key 8. So in terminal, we can hop over there, we can do an ls, and we can see there's a single file there called mixedin-key8.pkg, standard PKG to install the application. So now we have a PKG file. PKG files are still packaged, meaning we can't just like manually start analyzing it. We need to basically extract and pull out the files from the PKG. So my favorite tool for doing that static analysis of packages or PKG is something called Suspicious Package. This is a free utility online. I believe it's created by an application developer called Mother's Ruin or something kind of unique. But if you Google this, you should be able to find it pretty easily. And the link is in the blog. So what we can now do is we can, once Suspicious Package has been installed, we can right click on the PKG file from the DMG and click Suspicious Package. Again, this will allow us to statically analyze the files and the content of the package without running it, without installing that. So here's the UI, the interface for Suspicious Package. We can see it nicely shows all the files and where they will be installed. So we can see something called mixedinkey.app and then something called patch. Interesting. We also then click on the post-install tab in the Suspicious Package UI, and this shows us the post-install script. A post-install script, as its name implies, will be automatically executed during the install, specifically right at the very end. It's a post-install script. So we can see it doing a few things. First, it's going to create a directory, library mixed in key. It's then going to move that patch binary to this library mixed in key folder to a binary called toolroomd. Then removes that util folder, sets this toolroomd binary to executable via chmod, and then finally executes this. All right, so that's interesting. We should take a peek at this patch file, which is ultimately copied to toolroomd. If we run the PKG, and you want to do this in a virtual machine because you're basically installing malware, we see there's a password prompt basically saying installer is trying to install new software. Because there's this password prompt, if the user enters their credentials, this means now the malware will have root access and can perform more malicious actions. What we can do is we can run a process monitor while we are running the installer in the virtual machine to observe the installation process, right? And we expect this to see these commands being executed when the post-install script is executed. And sure enough, we do. So we see binsh being installed. We see the post-install script being executed. It's copied into the installer sandbox directory. And we can see the path to the PKG and some other arguments. So we can capture that via the process monitor. If we run a file monitor, I use fsusage. It's a built-in utility into macOS. We can see the actions of the post-install script occurring. Specifically, we can see it making the directory, that mixed in key. We can see that it then moving or renaming the patch utility to that toolroomd. So this is just us passively observing, dynamically observing that post-install script. And I oftentimes like to do that, right? If I see a script, I kind of read it first to get an idea of what it does, and then I'll run it in a virtual machine with some dynamic analysis tools to basically confirm that what I expect the script to do is actually doing. So we could either extract this patch or this toolroomd from the virtual machine, or we could actually extract it directly from Suspicious Package. Now, recall the Suspicious Package showed us that within the PKG, there was also an application called mixedinkey8. If we look at the code signing information of that, we can see it's validly signed by the application developers or by the company that creates this. This basically means it's a pristine copy of the application, assuming the hackers haven't, hacked that specific company, which is very unlikely. And this isn't too surprising, right? Oftentimes, when hackers are creating these Trojanized disk images of pirated applications, they will simply take the legitimate application and then package some external code. For example, as we saw here, this patch or toolroomd binary. So since the mixin key is validly signed, it looks to be pristine, we don't really have to worry about analyzing it all. However, we do want to focus our attention on that toolroomd binary because that's unsigned and likely is going to contain the malicious code. So the first thing we do is we run the file command. This just tells us what type of file the toolroomd or the patch utility is. Again, remember patch was copied to toolroomd, so they're one and the same. From the output of the file command, we can see it's a macOS 64-bit executable. Unsurprising, it's just a standard file format of executables on macOS. We can check the code signature. We can either use the what's your sign utility, or we can do it from the command line. If we do it from the command line, we can see that the code object is not signed. This just means that application, that binary, is unsigned. Next up, we run the strings command. There should be an S right here. I should fix that. But basically, what the strings command does is it will parse a file and extract all embedded ASCII strings. One important thing is you should always execute it with a dash command line parameter, because if you don't and you pass it a binary, it will actually only extract strings from certain sections. It won't actually scan the entire file. So this is kind of silly because we actually want to extract strings from the entire file. So again, execute it with the dash parameter. And then we pass it the path for the binary. In this case, it's that patch binary, because we want to see what strings are embedded. This is something I generally do first while I'm triaging the binary, because as we'll see, a lot of times embedded strings really give you a good sense of the capabilities of the malware, or provide insight into other pieces of information that can help guide analysis further along. So what do we see here? Well, first and foremost, we see a bunch of things that look to be obfuscated strings, encrypted strings. This is interesting. If we didn't know if the sample was malicious, seeing obfuscated strings is a red flag, right? It doesn't guarantee that something is malicious, but you know, a binary with obfuscated strings is probably something you want to take a closer look at. We also see what look like some command line parameters. We see some strings that appear to be related to some keying information. Interestingly, we see a path to a binary. And if you look closely at this, this is actually swaps. And if we kind of unswap it, it unswaps to effective idiot, which is kind of interesting. That's an observation another security researcher made. And then we also have some other strings that look to be related to key presses. So interesting. So this might indicate that the malware is doing some key logging type activity, which we'll see it actually does. Next up, we hop over and we run the nm utility. The nm utility will dump the names of symbols, including function names. Again, this is another static analysis tool I run because it can show you what API functions the malware may be importing and utilizing. And based on those, again, we can get a good sense perhaps of the capabilities of the malware. So for example, we can see it using some core graphic APIs. These are Apple APIs generally associated with creating a keylogger. We also see some very interesting Objective-C APIs, for example, ns-create object file from memory. This is very interesting because this allows a binary to create a executable memory image based on a file image. So normally when you're loading a file to execute, the dynamic loader takes a file path, loads it into memory, maps all the correct memory segments, resolves all the symbols, and then executes it. It turns out that there's an API to do that directly from an in-memory file image. So this is kind of cool. And we'll see the malware actually utilizes this to do very stealthy loading of second stage plugins or payloads. We then can also see the names of the functions that the malware has. These are the functions from the malware that the attacker has created. So based on the the function names, again, we can get some interesting insight into what it's doing. So we have some things like, TP encrypt, TP decrypt. Okay, this might be related to the ransomware capabilities. We have a bunch of React underscore function names, exec, ping, save, scommand start. Perhaps this is the names of the functions that handle remote tasking from the command and control server. A lot more, right? Root gainer main, loader thread, get host info, forensic send file, decode, is debugging, is virtual machine, right? Maybe some anti-analysis methods, persist executable, prevent trace. So This is really interesting because originally, we thought maybe this was just a basic piece of ransomware, but based on some of these function names, it appears that the malware may be doing more, right? So perhaps it's doing keylogging based on the utilization or the importing of the core graphic APIs. So you mentioned maybe it has the ability to do in-memory code execution because it's importing these interesting APIs. So you mentioned perhaps some anti-analysis. It has a function called isDebugging and isVirtualMachine. This is really helpful because as we start our dynamic analysis process in a debugger, what we can do is likely set breakpoints on these functions to make sure that they're not messing up our dynamic analysis session, right? It's not going to prevent us from debugging, for example. Other strings, right? Something like get host identifier or get process list might be indicating that the malware is doing a survey for continuing. Based on the persistence names and function names, it's likely that the malware is persisting as well. And as we mentioned originally, we think this malware has some ransomware capabilities. This is likely tied to some of the functions named that have encryption in them. So we've kind of done this triage basic static analysis, right? We extracted the files, we ran the strings command, the nn command, and this gave us a decent insight into the malware. But again, that's kind of a triage. So now what we're going to do is dig in a little more and actually first disassemble and then debug this malware because we really want to gain a comprehensive understanding of its capabilities. So what we're going to now do is we're going to disassemble the patch binary or that toolroomd binary. Remember, they're just a copy of each other. And we're going to kind of start at the main function and kind of kick through and look at what the malware does when it's executed. So the first thing it does is it looks for some command line arguments. And recall we saw these in the output of the strings command. So what we can do is we can look at code in the disassembler to see what each of these command line parameters mean. So the first one is silent or -- silent, and this appears to instruct the malware to run silently, for example, suppressing the printing of error message. So for example, we can look in the code, there are various instances where if the silent parameter was specified, it sets some variable to a 1. And if that's set, it'll skip, as I mentioned, things like printing out error messages. So this is likely a debug or flag that the malware author was using perhaps during testing. Likely she or he wanted to, test the malware, and so ran it without perhaps the flag so that error messages would be displayed if the malware failed during testing. Next up, we have the no root parameter. This again is passed via the command line, and if it's specified, it sets a value to 1. Various other places within the malware then checks this flag, and if it's set to 1, it takes a different action. So for example, skipping the request for root privileges. So if the malware finds itself not running as root, what it'll do is it'll show a fake pop-up asking for credentials. That may be something the malware doesn't always want, right? Maybe it's okay not running with root privileges. So it supports the ability to execute in this kind of normal user, limited user environment as specified by the -- no root parameter. Lastly, we have the ignore RP, and this basically tells the malware to ignore persistence. So again, there might be scenarios where the malware doesn't want to persist on the system. Persistence is a kind of noisy action, right? We'll talk about some tools and techniques to detect persistence. So maybe there's instances where the malware author just wants his or her malware to run once without persisting. So that can be specified by passing in the ignore RP command line option. So it's kind of interesting to see a malware be so extensible. It really kind of is starting to illustrate that this malware is rather fully functioned and fairly mature in a sense. So moving on, once the malware has parsed its command line options, it executes a function named isVirtualMachine. And if that function returns true, it exits. Now, as I mentioned, you always want to do dynamic analysis in a virtual machine because you're essentially running the malware, right? Like, don't do that on your developer machine, unless you have a dedicated hardware, a dedicated system for doing malware analysis, which would be nice. I use a virtual machine largely due to it's just simple. So Based on this function, though, as I mentioned, the malware will exit if it finds itself running in a virtual machine or if this function returns true. So we need to understand what this function is doing to see if we need to patch it out or modify it so that our analysis in the virtual machine can continue. So we take a closer look at this. I have the code, some disassembly, some decompilation from the malware. We can see it calls sleep with arg0. It then calls time, and then it does some checks to basically to do some basically comparison. So it actually, yeah, sorry, it calls time twice. So it first calls it right here, calls sleep, and then calls time again, and then does a comparison between this time and the sleep. And so what it's doing is it's then comparing the difference between the two calls to the time function and make sure it matches the amount of time that the system slept for. And you might be wondering why it would be doing this, and this is because it's trying to detect sandboxes, which often speed up the calls to sleep. So this is described in this quote here, talking about sleep patching sandboxes. A lot of malware, when run, will sleep for like an hour first. The sandbox obviously doesn't want to wait that long. So what it does is often patches the sleep API and basically has it return right away. So the malware is trying to detect that because in theory, if the difference between the two calls to time is different than the amount of time that was slept, this would indicate that this sleep patching is occurring, and then the malware could imply that it's running in a sandbox. So this means really this function is more of a sandbox check, not a virtual machine, right? In a pristine virtual machine, there's no hooking or modification of the sleep API. So this function will return false, which is good for us, which means we don't actually have to patch it or knock it out. So that's kind of nice. If we continue on, we can see the malware invokes a method called extract EI. We'll talk about this more, but basically it's looking for a certain flag or magic value, dead face in hex, at the end of a binary. If that is not found, which is not in the case of the initial malware that we're executing, it skips certain persistence logging. And we'll get back to that in a second. However, if we look at this code statically, even though it's not executed, we can see it executes a method called EI_stir and passes some of those obfuscated strings we saw in the output from the strings command. This is interesting because we can now assume that, or take a closer look, because it appears that this EI_stir function is probably the malware's string decryption or string decoding function. If we dive into this a little more, we can see it calls something called EIB string key. Okay, again, this is kind of, again, we assume that this EI_stir function is the string obfuscation or decryption routine. This lends to that assumption as well. And then ultimately calls something called secure decode, which eventually calls something called decrypt. So yeah, it's likely that this is the string decryption routine. Now, generally, I don't like to spend too much time diving into the details of the deobfuscation or the decryption algorithm because we can often simply avoid having to spend a lot of time understanding this. Because as we see, we can normally just set a debugging breakpoint after the call to this function and dump out the string that was decrypted. So this basically allows the malware to decrypt or deobfuscate the string for us, right? Instead of us having to statically analyze the decryption algorithm. Because especially if it's some custom crypto, that may take a lot of time. But we can at least dump the encryption key, which we see as this value right here. So I mentioned what I normally do is simply set a breakpoint after a call to the function. So if we scroll back a little bit, what we do in a debugger is we would set a breakpoint. Oops, did I go too far? For example, right here, or actually right after here. And then we could just dump this var50, which would be the now decoded or decrypted string. So again, it means we don't have to worry about how the malware is actually decrypting or decoding its string. In a debugger, we can just dump when it's decrypted. Now, a downside to this is we'll only decrypt strings when the malware invokes this function and our debugger breakpoint is hit. So this means if an encrypted string is only referenced in blocks of code that aren't executed, we won't ever see that decrypted value. And of course, we want to decrypt all the strings. So we know that the malware can decrypt strings, right? It calls this EI_stir function. So we just need a way to convince the malware to invoke this function on all the embedded strings. Turns out it's really not too hard. What we can do is we can create an injectable dynamic library that resolves the address of this EI_stir function. And then we simply invoke this function on all the encrypted strings. And luckily, all the encrypted strings are kind of in the same segment of the binary. So that's exactly what we do. So here's the code for that injectable dynamic library, whose goal is to decrypt all the embedded strings. So as I mentioned, the first thing we do is we resolve the function address of the EI_stir. Again, recall this is the decryption function that the malware uses to decrypt its strings. And then once we have that, we initialize some pointers. We're basically pointing to the start of the C string segment, which is where the embedded strings exist. So once we have those, we now have a pointer to all the encrypted strings in the malware's binary or in memory. And we just iterate through the entire C string segment that is, some amount long. I just hard-coded this because I'm kind of lazy. And we call this EI_stir function pointer on every single one. So if we execute this, we use the DYLD insert libraries to our decryptor library and execute the malware. This will cause our dynamic decryptor library to be loaded into the malware's address space. It will resolve the address of the malware's decryption routine and invoke it on all encrypted strings, dumping it to standard out. So we can see now there's a very large list of very interesting decrypted strings. And these are interesting because the malware in general, will encrypt or obfuscate sensitive strings. For example, command and control servers, because they don't want malware analysts to be able to access this information easily. So decrypting all these strings, again, gives us a lot of really interesting insight into the malware's capabilities. So we can see, for example, an address of a command and control server. We can see some references to files. We can see some commands to launch executables. We can see a bunch of regexes to file patterns that appear to match certificates, private keys, and cryptocurrency, perhaps keys and wallets. We have some more strings related to the run-in memory that we suspect the malware supports. An embedded property list, which is likely due to persistence. Maybe names of the malware where it's going to persist. So in short, a lot of really interesting things. Embedded command and control server, perhaps the name of the malware, security tools that the malware may look for, and then something that appears to be the ransomware message. So, and finally, file extensions that perhaps the malware is going to ransom. So simply from these decrypted output, we now have an even better understanding of the malware's likely capability. And this also allows us to now further our static and dynamic analysis, because what we can do is we also have the addresses of these decrypted strings that we can reference in, for example, disassembler and see where the code is referencing that. So for example, if we're interested where the ransomware routine is, we would go look at where this ransomware message is displayed, and we'd look for a cross-reference in the static analysis in the disassembler, and this would then be within the function, or at least the chunk of code that was responsible for alerting the user that their files have been ransomed. So this will give us a good spot to analyze, because a lot of times malware binaries can be very big, and it's very helpful to know where you want to kind of begin your analysis. So now we have the ability to decrypt all the strings. This gives us kind of a leg up. I do want to point out that another security researcher named Scott created a Python script that is actually capable of decrypting the strings manually. So he actually went through and reversed the entire decryption algorithm, extracted the keys. So very impressive work. I'm not as, let's say, committed as Scott. I'm just kind of lazy. I'd rather have the malware do this. But this is another approach, and definitely kudos to Scott. All right, so now we have all these strings decrypted. We can now continue our static analysis. We see the malware invokes a function named persistence main, which persists malware. However, before this function performs the persistence, it invokes various anti-debugging logic in an attempt to thwart dynamic debugging. This is fairly common. A lot of malware does this. It tries to detect if it's running in a debugger session with the assumption, the correct assumption, that if it finds itself running in a debug session, it's likely being debugged and thus analyzed by a malware analyst such as Patrick. So it should, exit or try to prevent that. This is pretty easy to track down in this malware. It has a function named isDebugging, so we can very easily go and see how it's doing its debugger check. And this is implemented at address 7AA0. If we look at the code, we see it invoking a system API, syscontrol, with these parameters, kernproc and getPID. And this basically asks the system for information about the process. And since the malware calls it with getPID, it's going to provide information about itself. When it returns, this API provides a bunch of structures that are now populated with information about the running process, including a info struct that has something called kppro. And there will be a flag there set to ptrace if the malware is, or if the process is being debugged. This is a common check. As I mentioned, a lot of malware does this. So I had a slide from previous malware analysis. We can see this is what it looks like in assembly code, and then this is how it looks like in pseudocode. Again, here's the call to that syscontrol call. And when that returns, the malware will check if the ptrace flag is set on the process. So if the malware detects that it's running in a debugger, we can see right here it calls exit. So we need a way to subvert this logic because obviously we want to keep debugging. We want to keep dynamically analyzing this sample. The easiest way to do that is simply set a breakpoint on this instruction right here, which is the comparison of the function call return, and basically change the value so that this jump instruction is taken and so the malware doesn't exit. So it's pretty easy to do. In the debugger, we set a breakpoint immediately after the isDebugging function. That breakpoint is hit, we can dump the return value from the function. We can see, yes, indeed, RAX is set to 1. RAX will contain the return value from the function. 1 meaning true in this scenario, meaning the malware has detected that it's running in a debug session, which is unsurprising because we are debugging it. What we then do is we execute the regwrite debugger command, and we set the register to 0. This is basically saying, no, we're not debugging. We then allow the malware to continue, which means this comparison will hold, and this, or rather will not hold, and this jump 0 command will be executed. So what we've done is we've just kind of subverted the malware to skip the check to see if it's in the debugger, which allows us to keep debugging. Unfortunately, the malware then contains more anti-debugging logic. It has a function named preventTrace, and this seeks to prevent tracing or debugging by calling ptrace with ptrace deny attach. We can see that in the disassembly of the preventTrace function within the malware. This is another common anti-debugging technique that a lot of malware will implement. So if you're looking at Mac malware, you're likely to encounter that. Ptrace is obviously a system call. The ptrace deny attach is an Apple-specific flag or parameter that basically tells the system to disallow processes from being able to attach if the process is already running, or if the process is already running and a debugger is attached, it will automatically execute. So we don't want this code to run because it will essentially kill our debugging session. So the easiest way to do that is simply set a breakpoint on the call to the function, the code that invokes the prevent ptrace. And we can do that right here. You can see here's the call. This 7C0 is the call to the prevent ptrace function. And then what we do is we use the regwrite command, and instead of modifying the RAX register, we actually modify the instruction pointer, which changes the instruction that's about to be executed. Instead of calling the prevent trace, it'll just call the very next instruction. So this allows us to basically skip over the entire function call altogether. So now we can continue our dynamic analysis, unperturbed. The next thing the malware does is invoke a method called kill unwanted. And what this does is it gets a list of the running processes, iterates through all of them looking for common security tools. For example, Little Snitch, Kaspersky, Bitdefender, something called McAfee with 2 Fs. And if it finds processes that match that, it will invoke the kill API to execute, to kill these processes. This is just a mechanism to probably prevent detection or persistence. So kind of interesting to see malware taking kind of offensive capabilities against installed and running security processes. All right, so now the malware has done all that, it finally calls the persistence logic. And what we can do is we can dump some of the values. These are decrypted strings, and we can see these are the paths likely related to the persistence. Kind of jam through the specifics of the persistence, but basically if we run a dynamic analysis tool like a file monitor, we can see it creating files. For example, something called com.apple.questd or tilde library com.apple.questd. And if we MD5 these, we can see that these are both the same copy of the same binary, which again is this tooled binary. It's a malware basically making itself. So the malware makes 2 copies of itself in the library and the tilde library directory. Once the malware has made a copy of itself, it'll persist itself as a launch item. And we can kind of pop through the code and debug some strings. If we jam down a little further, we can see it decrypting an embedded property list file. And once it writes it out to the file system, we can examine it fully. And we can see that the property list that's created is something called com.apple.questd.plist. In this case, it's in the user's launch agents directory. And since this property list has the run at load key set to true, this tells the operating system every time the user logs in, please execute whatever is specified in the program arguments key, which is the path of yet another copy of the malware, com.apple.questd. And note that it also passes in the silent flag. So in other words, this is the malware persisting as a launch agent. One of my tools, block monitors for persistence, so we'll detect when the malware goes to persist. Basically monitors for the creation of new launch agents. Interestingly, if the malware is running with root privileges, it invokes a method called install daemon, and this time it persists as a launch daemon. So it actually creates another property list with the same name, but in the launch daemons directory. So this basically means the malware has persisted twice if it's running as root. It then, interestingly, or rather unsurprisingly, launches these launch agents. So these launch items are running. If it's root, there's going to be 2 copies, the launch agent and the launch daemon. And then it makes yet another copy of itself via a call to create rescue executable. This is just another copy of the malware that will be running kind of in the background. And it's interesting because this is just another way that the malware kind of ensures that if you, for example, kill the main malware process, it can detect that and basically make another copy of itself. And here we can see the malware via a process monitor launching that additional copy of the malware, which is in the user's library directory, and it's a randomly named binary. So this kind of wraps up the first part of our analysis. We basically saw its infection vector, which was Trojanized pirated applications. Talked about its persistence, right? Launch agent, it's running as root, login daemon as well. Then we also talked about some of its anti-analysis logging. So now we're going to dive in and we're going to continue and look at actually what the malware does once the system has been infected and persisted. So the first thing that it does is very interesting, is it actually infects other binaries on the system. So in other words, it has the ability to execute viral infection. And to me, this is really interesting because as far as I'm aware, this is the only, at least in recent memory, Mac malware that has viral capabilities. Normally when malware gets on the system, it creates a launch agent, a launch daemon, calls it a day. It doesn't actually modify other binaries on the system. Interestingly, the malware does this by spawning off a thread and invoking a method named loader main. What this does is it first calls a method get targets, which gets a list of executables, and then it calls something called append EI. And we'll talk about these functions in a little more detail. So first, the get target function is executed. It's given a root directory, to start with, /users. And what it does is it recursively generates a list of files. For each file that is encountered, it invokes a callback or filter function called isExecutable to see if the file is of interest. That is it a target that the malware can virally infect? If we look at the isExecutable function, it first checks if the path contains .app. And if not, it continues onward and checks if the binary has one of the 4 magic headers, magic values that indicate I believe, a universal binary or a macOS binary. So this is basically the malware checking if the file is a target for infection based on its file header, right? Is it basically a macOS file? It then calls the append EI function, and this is the actual viral infection function. So now the malware has identified targets of interest, binaries on your system, on the infected system. What it will do is it will open and read the contents of the source and the target files. The source is the malware, the target is the file it's about to infect. It then writes the content of the source file, which is the malware, to the start of the target. So it puts the virus, the malware, at the beginning of this code. It then rewrites the original code of the target program immediately after that. And then it appends a trailer, an infection marker called deadface. Recall in the first part of this talk, we mentioned that the malware checks for this. The original version of the malware didn't have this because it's a pristine copy of the malware. But any binary that is infected will have this trailer at the end, so that check would then hit. So once an executable file is infected, since the malware has inserted itself at the beginning, the malware's code will actually run first whenever the binary is executed by the system or by the user. Of course, the malware wants to ensure that nothing is amiss, so it should run the original code as well, right? If you've double-clicked a binary on the desktop that, plays some music, you expect music to play, right? If it didn't, you might suspect something is amiss. So what the malware does is it detects that it's running in an infected file, goes and finds the content of the infected, the original file, which has been kind of put at the end of the file, writes that out to a new file called dot, and then the original file name 1, and then sets that to executable and executes that. So we can see that I created a file called infect me on the desktop. I ran the malware then went to infect that. When I then went to manually run the infect me binary, which has now been infected, we can see via a process monitor that behind the scenes, the malware has created a restored copy of the original binary called infect me 1 with a dot, and then executes that. It's kind of interesting. So since we understand this viral routine, this means 2 things. First and foremost, it means that simply removing the malware's launch agents and launch daemon will not disinfect the system, right? And that's why viruses infect systems, to make it very difficult to disinfect. So this is interesting. Again, this isn't something we normally see Mac malware do. Basically, this means if your system is infected, it's burn it down, right? I mean, it's going to be very difficult to disinfect it. However, we could write a disinfector. We could simply scan for this dead face marker and then basically parse the trailer, which has the offset to the original code, and then basically rewrite or restore the original file ourselves. So it would be possible to programmatically disinfect the system if we were so inclined. But really, if a system is infected with EvilX, it should just be wiped and macOS should be restored. So that's the viral infection capabilities of the malware. Very interesting. Next, we hit file exfiltration. So a neat capability of this virus is its stealthy exfiltration of files that match certain regular expressions. So the malware spawns a thread called forensics thread which connects to the command and control server, reads a file that contained the address of the malware's remote command and control server. It then generates a directory listing. We can see in a debugger when I run it on my VM, it's all the user's directory. The directory listing is then uploaded to the attacker's command and control server. So the attacker now has a full directory listing of your files on the system. And it does this via the forensics send file function. The malware then invokes the get targets function, which we discussed earlier. However, this time it passes another callback, which is called isLFSC target. And what this simply does is for every file on the system applies a regex to see if it matches to one of these decrypted regex that we saw earlier in our decrypted string output are related to certificates, private keys, and cryptocurrency related files, key.pdf, wallet.jpg, etc., etc. So this means the malware is basically sniffing the system for private keys, certificates, and cryptocurrency keys and wallets. So we can see that once the a file matching one of these regexes are found, it will call again this forensic send file to exfiltrate that specific file to the attacker's command and control server. And we can confirm this in the debugger. I created a file in my virtual machine named key.png, which would match one of those regexes. And sure enough, we can see that the malware found that file, and then it's going to send that to the command and control server. So this just validates and confirms, yes, indeed, the malware is scanning the system and exfiltrating files that match those regular expressions. So again, if you're infected, you have to assume that the malware has all your private keys, wallets, and cryptocurrency keying information, if those are stored on your Mac. Next up, the malware also spawns a thread to do some persistence monitoring. This is interesting because it appears that the malware is doing some basic self-defense via KQs. I'm not going to go through kind of all the details of this implementation, but basically it tells the system it's interested in watching itself, and if itself is deleted or removed, as long as it's still running in memory, it will get a notification because it's registered for a watch on itself, and will go and repersist itself. So this is interesting. We can observe this passively in a virtual machine that's been infected. We remove the main malware binary. This is the one that's persisted and referenced in the launch items, either the launch agent or the launch daemon. We do an ls command to confirm that the file has been deleted. If we then spin up a process monitor, we can see that the tool roomd binary, which is the instance of the malware that's also running, detects that the file was deleted and writes it out again. So again, if we do an ls, we can see the malware has repersisted. This is very interesting, right? This is basically, again, showing that this malware is decently sophisticated and mature, but it's actually watching itself and has some self-defense capabilities built in. So if anyone removes it, the malware can repersist itself. It's very, very sticky. Next up, we have remote tasking. So the malware also supports the ability to execute a small set of powerful commands remotely that really give the remote attacker the ability to fully command and control an infected system. So what the malware does is spawns off a thread, connecting with the command and control server, gets the address of that. If the primary command and control server or this address is down, it uses a hard-coded IP address, 167, et cetera, et cetera, et cetera. It then invokes the get host info function, which basically generates a survey about the infected system. We can see it contains the username and information about the system. For example, the version of the operating system, et cetera, et cetera. The survey information is serialized and then sent to the attacker's command and control server. If we look at the malware's disassembly, we can see that the response from the command and control server is something called check command. Cool. Interestingly, it appears that there is some information, perhaps a checksum in this response, that is logged to a hidden file, .shcsh. which perhaps means this is a good indicator of compromise, and may have some other information about what commands were executed. So any tasking that's received as a response from the command and control server is handled via a function named dispatch. What this basically does is checks first it checks that some checksum matches, and then actually checks if the command is if the command that was sent to the host is specific for the host or not. And it does this by first checking if the response from the server offset 10 contains hex 200. It also then checks that at offsets, another offset is some other hard coded value. And most interestingly, at offset 14, it checks that the first byte of the infected system's MAC address is not 0. It checks if it matches what's in the response from the server or if it's not 0. So that's kind of interesting. So that MAC address check is kind of the most interesting one, because this means that the attacker either knows the first byte of the infected system's MAC address, because nowhere in the code is the MAC address actually sent to the server. So it means the attacker has some a priori knowledge of the systems he or she is targeting, which is kind of interesting. Or it could also mean that the attacker only wants commands to be processed on an infected system where the first byte of the MAC address is 0. I don't know what that means, in the sense I don't know what systems have a MAC address at 0, but it was 0 on my VM, but not on my base system. So there's some interesting things there. I don't fully have a good answer yet for that, but the fact that the malware is checking the MAC address and seeing if the command kind of matches that is interesting. Again, especially since no information about the MAC address is actually sent to the attacker, for example, in the initial survey. So that's interesting. And it does that via the check if targeted function. So again, are certain systems targeted? Who knows? All right, so now let's look at what tasking or what commands are allowed, what are supported. So first off, there's something called react exec. And this contains the logic to execute data received from the server in memory. So this goes back to the APIs we mentioned earlier, NS create file image from memory, et cetera, which allow the system to take a file image in memory and convert it to a executable in-memory image that can then be run. So I talked about this at a talk at Black Hat a few years ago. Apple actually used to have sample code. They don't have this online anymore, but if you Google memory-based bundle, and this is a very stealthy technique because it means that malware can, for example, pass down an encrypted payload from a command and control server, decrypt it in memory, and then directly execute it in memory using Apple APIs, right? It doesn't have to do all the in-memory loading and symbol resolving itself. So very, very stealthy and kind of an advanced capability to see. The react save command decodes data received from the server, saves it to a file. Pretty basic. The react start is just a no-op, not implemented. The react key command, which is a value OX8, starts a keylogger. We talked about seeing some keylogger related strings in the strings output and the NM output. So this is where these API and keylogging specific functions come into play. So specifically, the malware will invoke the core graphic CG event tap enable, which will start something called an event tap. It's just basically how you do keylogging on macOS. The interesting thing is, though, in the callback routine that is invoked in the malware every time a key press is pressed by the user, it's just printed out. It's just a call to printf. So it's not like written to a file or sent back to the attacker's command and control server. So perhaps this part of the malware is not quite done yet. The react ping function basically just compares a value from the server and responds back with hi there. So it's basically just a ping pong kind of thing. One very interesting piece of information about this method is in subsequent versions, the ping string has been updated to instead say "Hi Patrick." So it seems that the malware author was paying attention to my analysis and gave me a shout out. So, you know, that definitely made me smile. So, you know, wherever the malware author is, mahalo for reading my blog and giving me a shout out. That was always, you know, one of my goals as a malware analyst, you know, see my name in some malware. Moving on, the host command is a no-op, doesn't do anything. And then finally, we have the react s command, which simply executes a command from the server. So we can see the malware supports this kind of basic command and control tasking, the ability to execute in-memory payloads, kick off the keylogger, download a file, execute a command. This really gives the remote attacker complete access to an infected system. And then finally, we have the ransom capabilities. Basically, what the malware does is it enumerates all the files on the system, starting at the user's directory. And for any file that matches one of these 20, 30 or so file extensions, it will ransom them. Not going to go through all the details of the ransom utility, the ransomware routine, but basically it calls a function isCarve to check if it's already been ransomed. If it hasn't, it goes ahead and encrypts the file via a call to EIP encrypt. It then shows this message to the user, or rather saves this to the desktop. It also pops up this modal window and reads this. It's kind of creepy, you know, your VM starts talking to you. That basically says your files are encrypted. As I mentioned, I wrote a utility that generically looks for the rapid creation of encrypted files by untrusted processes. And this tool thus can generically detect when the ransomware starts. Basically, it can detect and alert you when one or two files are encrypted. It will suspend the process and basically say, hey, just to let you know, something is encrypting all your files on your system. And then you can either allow it or terminate it. Now, we might be wondering about file decryption. Interestingly, there is a function named uncarveTarget, which appears to be able to unransom a file if you give it a file and the decryption key. However, there's no cross references to that function. Meaning nowhere in the code is this function referenced, right? It's not like the attacker can send a command then to execute that. So that kind of also is interesting. Also, it doesn't appear that the encryption key is sent to the server. So it really seems like the attacker has no intent of actually decrypting the file. Some researchers at SentinelOne, though, analyzed the encryption routine, and they found out that it used some custom crypto, but basically did use a symmetrical encryption key that they were able to ascertain. And so they published a decryptor for that. So good news if your files are encrypted. I would recommend not paying the ransom because it doesn't appear to actually decrypt that. And it's interesting because in the README now, it basically says make a payment to this Bitcoin address. It doesn't like give you an address or any other way of communicating with the attacker. And as I mentioned, there's no cross reference to the decryption routine. So it really doesn't seem the attacker is going to go ahead and decrypt your files for you. So, but luckily, as I mentioned, the SentinelOne researchers released a decryption utility. So it's interesting, right? There's the discussion is, why is this malware even ransoming files? Is this a cover? Is it a wiper? And that's a really good question because as we saw, it has the ability to, do things like execute in-memory payloads, and it has tasking that's looking for specific MAC addresses, which would indicate it's very, very targeted. My guess is that the attackers are probably trying to infect as many users as possible. And certain targets that are of interest, they're not going to trigger the ransomware logic. Other targets, though, that are perhaps to hide the malware or make some money, they said, hey, screw it. This target really isn't of interest. We might as well go ahead and ransom all the files, and maybe we'll get some Bitcoin out of it all. Whereas targets that are of interest, they probably don't encrypt the files and instead just keep using that command and control server to maintain covert or surreptitious access to those infected files. So that wraps up kind of the a whirlwind tour of EvilQuest. we kind of thought it was just ransomware at the time, but digging into it more, we really saw it had some file exfiltration capabilities, remote tasking capabilities, and yes, ransomware logic. As I mentioned, some of the free tools I create, Block and Ransomware, can detect and thwart this attack, and did so with no a priori knowledge, which is kind of neat. Finally, we have some indicators of compromise. These are kind of the files to look for on a system if you think you might be infected. But I do want to reiterate, if you are infected, that means the viral logic has also executed, which likely means other binaries on the system have been infected with the malware. So best bet is to simply wipe the system and fully reinstall macOS. So that's a wrap. Thank you again to Matt for organizing this conference, and thank you all for listening in. I think we have some time for some questions if there's any questions to be had.
Thanks to you for joining again. When you mentioned the Sentinel-1 tool, I just got lost and I started to Google it and to have a look at it. Do you know how it works? Like, is it because like the encryption of the file was weak, or because it seems like there's this assembly file where they're just like hard coding a bunch of function like TDP crypt, like iscarve, like I'm not sure if they actually really wrote some function, if it's just like copy paste of some hard coded functions and then they can just decrypt them.
Yeah, that's a good question. I haven't dug into it that close. I did briefly look at the encryption logic, and it did seem to appear to be generating some random keys. It was calling time, SRAN, and stuff like that. So I was surprised when they were able to figure out a decryption routine generically, because I thought the key was randomly generated, and as I mentioned, not
machine specific or something, right?
Yeah, so I don't know the details of that. They promised to open source it. I'm not sure if it's open source.
It is open source actually. They published
awesome.
it 8 days ago. I'm checking the source now. It's a guy called Julien Pierre Evors who worked on it apparently.
Another French guy.
I think so. I'm checking his GitHub. He's from Paris. Yeah. I'm telling you, like French people, they spend like all of us spend our time like cracking software when we were teenagers. So
yeah. So I kind of looked at it and I was like, this looks too hard. And I think it took them like a week of like super, nerdy reversing it. So like mad kudos like that. I was very impressed. It's not something I was going to do. So.
Yeah, but that's why I'm do you know if they wrote a blog post to give a bit more detail about the encryption also?
I didn't see one. I mean, they published a blog post kind of on their technical analysis, kind of looking at the new versions. The new version really didn't change much. It added a shout out to me, which I thought was neat, but the functionality kind of stayed the same. But no, it would be very interesting. Hopefully there's one forthcoming, because I would be very interested, because a lot of the crypto routines are pretty extensive, right? It's not like a basic XOR. So either there's some custom crypto or some a standard encryption algorithm with, modified constants or something. So, and maybe that's where the weakness was introduced. But yeah, it would be very interesting to dive into that deeper.
Yeah, it's kind of cool every time like some people manage to write a tool, to recover files. It's like you're like, oh, so because the question is like for ransomware is like either you do it on purpose to make it weak, for like XYZ reason, or I don't know, you're just really dumb, because there's already like models of stuff, like how can you like but I guess it does make sense anyway to not make it like bulletproof, because at least if people can still recover, maybe if you get arrested, it plays in your favor, because otherwise it's probably like you were saying, like, is it a wiper or not? And then if it goes into wiper, it's like pure destruction. And I think that's if you ever get arrested, you probably get. Even if you get arrested and files can be recovered, you're probably gonna get destroyed. But
sure.
I think it's
pretty interesting.
I'm very curious about it. Like
because this malware author.
Is it one guy or is it like some stuff that had been shared across multiple teams?
No, it's the first time I've seen it. So that was the interesting thing. A lot of Mac malware we see uses a lot of kind of shared code, or it's like not written that well, right? It's got like a lot of like Linux APIs instead of like, the Mac specific stuff. So this malware author though is intimately familiar with, coding Mac on the Mac, and it's a very comprehensive and well-written piece of Mac malware. So yeah, it's very, it's doing in-memory code execution using KQs to monitor files. Like, this is a very competent Mac malware author. So the fact that the ransomware piece is kind of subpar is very interesting, because as you mentioned, it defeats the purpose if you're using a symmetric key. And by now, I would imagine that ransomware authors, have, it's not that hard to correctly ransom files, right? Using like public key exchanger or whatever, a random key that's sent to the attacker. So yeah, I've either seen that this ransomware logic was a distraction or just not really that thought through, because also the
guy left the symbols also, right?
Yeah, the symbols were in there, and also the payment was like
I was like, what the hell?
US for ransomware decryption, which is really low. So yeah, it's interesting. So
nice. I mean, like, why not? If you have like your symbols, I don't think it's not preventing the ransomware to work.
Yeah,
but I thought it was quite funny actually, because when you showed it at the beginning, I was like, oh, is it like, do they share like symbols for like ransomwares now? I was like,
it made analysis far easier. It's like, having a function named is debugging or like encrypt files.
So
that was nice. So, maybe then this malware is maybe a work in progress, right? We saw the keylogger logic not be complete.
That's very possible. I mean, also once you get in that business, usually you don't stop at one,
yeah. I don't. The other thing about the ransomware is, I think someone checked the that Bitcoin address, and it showed that 0 people had paid. So that either means it was wildly unsuccessful, or again, it was just kind of a cover or a wiper, and the ransomware, the malware author actually never really expected that to make any money. So
is it quite common to see ransomware on macOS now?
No, this is only I would say the third real sample. We had KeyRanger. I believe in 2016, which was, a fully functional ransomware, but again, its goal was simply ransomware. We had another one called Mac Ransom a few years later, again, just doing ransomware. So over the last few years, we really haven't seen it, which is interesting. So that was kind of the interest when I saw this to really dive into it. It was just like, hey, this is, not something we see every day. And as I started digging into it more, I was like, wait a minute, this is not just some basic ransomware. It's really got a lot of very advanced capabilities. And the ransomware piece is either an afterthought or a cover, which is interesting. But it does, encrypt files. So it is ransomware.
Yeah, it does the job. So, I mean, most of like, even on Windows, most of ransomware are like not really advanced. It's usually very redundant. And then it takes like a few years for EDRs to say like, oh, we're blocking against ransomware because the thing is encrypting like more than 1,000 files. It's like,
and that's why the ransomware utility I wrote, I think it was in 2015. It was like, I was like, does this tool still work? Because it really hadn't had a lot of ransomware to test it, but Mac ransomware is pretty basic. So luckily those generic heuristics still work 5 years later. But yeah, the other thing was the in-memory code execution. And I know memory forensics is a very interesting topic that's near and dear to you. This is an example where, as you mentioned, kind of an EDR product or security tool will have no insight into what the malware is basically downloading and executing, unless you have a kernel extension, which Apple is deprecating. So it is unfortunate that Apple is kind of doesn't really provide an easy way for security tools to examine memory of remote processes, and attackers know that, and it does seem like they are kind of taking advantage of that. By this is the second piece of malware this year we've seen leveraging that in-memory code execution specifically as a way to be incredibly stealthy and bypass the abilities of security tools.
That's really a shame. So there is no alternative, huh? So there is no kernel extension, and the APIs that they're giving for like monitoring are like a very high level, right?
Yeah. So via kernel extension, I'm sure you could still do that, but those are basically deprecated and going away. So I'm surprised they're even supported at all in macOS 11 that's coming out. But yeah, unfortunately, the endpoint security framework, my understanding is it doesn't have, I've looked, doesn't provide the opportunity to do that. I'm guessing what Apple is going to do is very shortly, especially on their new ARM platforms, is disallow in-memory execution. So they're probably like, hey, you guys, security tools don't need this capability because it's something we're disallowing shortly anyways.
Yeah, I mean the ARM stuff I think is gonna take a while because there's still a lot of like non-ARM stuff which is gonna work. Because when I did my Windows exploit for ARM64, I mean it pretty much worked exactly the same way as you would do on X64. There's just some like minor differences, but it's not like crazy like different that you're like, oh wow, like that's nothing works, like even like for like a page table translation, it was still the same thing,
That's awesome.
So it's
make
not
your exploit writing easier.
yeah. I mean, like I didn't know anything about ARM64, and I wrote everything in 2 weeks. I took that SMB Ghost exploit, right, and I wrote an ARM64 version.
That's badass.
Yeah, I presented it at the last Upcode actually.
Nice.
And and that was not that not that different. So I would expect probably something similar on Mac. I know on Windows because of the what do they call it? The HVCI, like hypervisor code integrity, which is enabled by default now on on Windows, so including on ARM. On the ARM version I had, it was not enabled by default because it was in a updated Windows, but now it is by default. So unless they do some like secure like virtual memory type of thing like there is in Windows now on OSX, I guess they're still gonna have a bunch of problems. But yeah. And by the way, I wanted to ask you also your tweet about the X-Protect because I didn't know what X-Protect was.
Oh, sure.
And so if I understood correctly, so you got the signature from the Apple database, right? So X-Protect, I guess, is the Apple antivirus.
Yeah, exactly. It's not something Apple really likes to talk about because it, brings awareness to the fact that Macs get malware, which Apple doesn't really like to talk about. But yeah, basically, in every version of macOS, there is X-Protect, which is a signature-based AD. They have recently started using Yara, which is kind of interesting. And so what they do is every now and again
the Yara signature that you posted in your Twitter screenshot is directly from X-Protect?
Yes.
Oh wow! I thought you had to like reverse the database and do like a Yara.
No, they just.
Oh wow!
There's like a xprotect.yara file that you can just grab. So in the context of EvilQuest, they pushed out one signature and then a week or two later updated it because there was a new variant and their initial signature wasn't that good of a Yara signature. And then the other tweet I had about it is the problem is when they push out a signature, they never say what it is. So the most recent one, right, they just name it Mac something, something, something. We can extract the Yara signature to see what they're looking for, but they don't share information about the binary or the file, which to me is a little unfortunate because it would be great if, they were well, I'm not gonna go on this rant right now, but it would be nice if they shared, more information about the malware they were seeing and perhaps shared a hash or binary, because the latest X-Protect update contains a new signature for a compiled AppleScript malware. And so we can see what the signature is looking for, but nobody has any other information about this file, right? It's not on VirusTotal. None of the security researchers or AV companies I've talked to know about it. So, Apple has this information. It would be great if they shared it with other security researchers. But for now, we're basically stuck, monitoring X-Protect signature database or Yara file. And then when an update comes out, at least we can see what the Yara signature is. But unfortunately, a lot of times it's just a dead end because Apple isn't as communicative as they could be.
And is it like one master Yara file with X-Protect?
Yeah.
Or is it a bunch of, and how many signatures, how many rules are inside the latest update?
I think there's maybe like a few hundred. Let me see if I can pull this up and share it on my screen.
Yeah, that would be quite cool actually. Like if you take like but I don't know if you can have an historical like update, for like all the version like at every quarter, and you map it as a graph, to see like how many like new signatures. Because
Yeah, that would be, yeah,
it's
exactly.
still
And
like
over
it's
time,
still like high enough that it's kind of cool to watch the growth, and at the same time it's not like a big number enough that like that's still relevant to do it.
you
Because
see
when
my
did they
screen?
introduce? Let me put it up now. Yeah, I see it now.
So the file is xprotect.yara. It's in System Library Core Services. And if we look at it, it's funny they have a rule for PE binaries too.
Yeah.
But then you can just see, let's see, I guess if we do a word count on this, maybe we can see how many signatures.
Oh, just on the rule space, I guess.
Yeah.
Oh yeah.
Word count. I don't know how to do this. Word count. Grab it. Yeah. Okay, so 58 signatures.
Okay, that's and when did they introduce the xProtect? Was it last year?
No, it's been around for like 5 or 6 years.
Oh, is it the same thing that they use when the Zoom had the vulnerability and that remove a file or not? Oh, it's not.
So they have another AV product called MRT, which stands for Malware Removal Tool. And so what xProtect does is xProtect runs every time a file is launched. So it's kind of like an on-demand scanner. What MRT does is it actually will scan the system, and if it detects files that match its signatures, it will actually remove them. So what Apple did in the case of Zoom is they pushed out a signature for Zoom, or specifically the kind of remote component of Zoom that had that vulnerability, and then silently removed it. So this was kind of crazy because, basically it illustrated that Apple has the power to do at any time, remove any file they want from your system, which is slightly insane. MRT, though, the signatures for that are compiled into the MRT binary. So you actually have to go and reverse engineer that to pull those signatures out.
And okay, so an MRT is the new thing, right? All these MRT?
MRT has been around for 5 or so years as well, too. So
okay.
Yeah, so that's in we do like strings. I think it's in System Library Core Services. MRT.app. No?
By the way, Spender had a look at the Sentinel-1 stuff, and he says the seed is hard-coded at the end of the binary. That's the mistake they made.
Okay.
Oh, no, in the not the binary, the file actually. They left the seed in the.
They have this like 80 hex 80-byte trailer that they appended, so it makes sense that the key information is in there. So.
And he's saying also too bad in the PE signature in the xProtect they made a mistake because for the ELFNU field it does not have to be a free C. It can be like any number because it's just an offset, like they can just
exactly. So but yeah, the xProtect stuff is interesting. It's a good way to kind of get insight into Mac threats because you can see when Apple pushes out an update. Yeah, it would be great if they shared that information more. Because maybe the AV companies want to push out a signature to their users, but Apple basically, I think their mindset is, hey, we push this out to our xProtect databases, and that covers all Macs, so no one else needs to worry about it. Which is what it is.
Yeah. So there's no way there's no quick way to know like how many signatures inside MRT, huh? Outside of diffing like each MRT version, because
correct.
It's
it's super annoying. Let's see. Okay.
Someone in the chat sent that article from Phil Strokes on running diff on the Apple MRT app. I don't know what that is, but
he provided kind of like how you go through the how you kind of go through and grep or parse out the signatures. So.
Oh, got it.
Contents. So if you see on my screen, I usually just dump the strings, and then it's also written in Swift, which makes it really annoying. But they have like family. You can see, for example, they have one for mommy. And so they used to actually embed the names of the actual malware in here. So we can see Xcode Ghost, Eleanor, Wire Lurker,
I see.
Eureka, Netwire, Bunglador, Fruitfly. So then you go and look for basic cross references to that to find their signatures. You can see Hacking Team, Proton, Snake. But yeah, basically you would have to
Pegasus B, Pegasus C. I'm kidding. But imagine in the July update, you know.
That'll be funny. Well, look, we'll keep an eye on it.
Yeah, but you know, like if you just like keep the counts and you just like map, you know, as some short, and you just do like, you know, like a D3 like JavaScript short, and you just like put a CSV,
Definitely.
you know, and update your CSV, and you just have a web page that keep track of them, because it's not like there's like tens of thousands, so it's still like interesting to see like the growth rate between each quarter, I think.
Yeah.
Because especially if you're saying that's the third like ransomware you're seeing, it means okay, like maybe people are starting to actually do ransomware more seriously on Mac, you know. So it would be interesting to monitor like those trends.
Yeah, no, it'd be super interesting, because I think Apple has the best insight into, you know, threats and trends. I'm not sure. I know they subscribe to certain threat intel feeds and stuff like that, but they have access to a lot of private information about malware trends and stuff. So looking at MRT signatures and XProtect signatures is kind of the best way to gain insight into Apple's insights indirectly. Because when they push out an XProtect signature, it's basically, or an MRT update. Well, if they push out an XProtect signature, it's basically an acknowledgement that this is a prevalent threat that they're seeing, they are seeing targeting Mac users. So they basically want to protect Mac users.
Yeah.
When there's an MRT update, that indicates that there's a significant infection that they want to actually proactively disinfect the systems.
Oh, that makes okay. So that basically, if it's in XProtect, it means it's probably not on VirusTotal. If it's in MRT, it is in VirusTotal.
Yes, exactly. So a good example was Fruitfly. When information came out about Fruitfly, the FBI had already arrested the alleged creator of that malware. So there was no threat of it spreading anymore. But it was on thousands of systems. So what Apple did is they pushed out an MRT update, but did not push out an XProtect update, because they basically said the threat is, you know, there's no threat for it to spread more, but we need to disinfect systems that it's already on. So that kind of provides that. So, but yeah, it is interesting though that when they update MRT, they have to like push out an entire update of the binary, right? It's like, you know,
it's a bit strange. Maybe because they're afraid of people like modifying the binary or something, just so they can send the binary and the database at the same time. I don't know.
But XProtect stuff is SIP protected, so in theory, it's
yeah.
I think it was just, you know,
two different teams.
You know, a small project that's, you know, an intern, or maybe not an intern, but like, you know, it was like, okay, hey, we should have a simple utility that can clean up these 3 or 4 malware samples, and then it kind of grew and grew and grew, and so they're just kind of pigeonholed into that approach.
Yeah, that would definitely make sense. Probably like, yeah. But if you're saying it's been already like 5-6 years, huh?
Yeah. I think it was. Yeah, it's been around for a while. So.
Okay.
Yeah, Apple doesn't really like talk about it because it, you know, brings attention. So.
Yeah, because for some reason I thought it was like released just for like the Zoom stuff.
No, they've. I think that was the first instance of them using it to remove non-malicious code, right? I mean, no one cares if you release malware, but you know, Cupertino automatically pushing out an update to remove components from your system, like, yeah, I mean, that's a pretty. I don't know. That's interesting.
Yeah,
it's a pretty aggressive step.
But yeah. Yeah, I don't know if we have more questions in the chat. I do not think so. Yeah, like outside of Spender, where he looked at the GitHub repository and figured out all the algorithm was working in less than a minute, you know.
Yeah, I'll definitely have to take a peek at that.
Yeah, that's pretty cool. Well, thanks for the presentation. It was really cool, and yeah, really good to be able to see like part 1 and part 2 in one block. You know, I think it's really awesome because, like you said, you know, there's not that many ransomware. It's great to get a good peek at it, and also to get all the content at once. And yeah, presenting a blog post actually, I think is a pretty good model. I did that 2 weeks ago also. I think it works great, you know. So don't do the work twice.
Awesome.
Yeah.
I mean, it kind of allowed me to kind of rapidly present, you know, existing content.
Yeah. Kind of, no, I think it's awesome. I did it also like 2 weeks ago. It works great. Yeah. Also, like if you cannot present your blog post, it means you are missing some parts to it. So you're like, oh, maybe like you have to rewrite it, you know. So it's a good exercise too.
Yeah, definitely. It's like, it's very comprehensive. So, well, thanks again for having me on. I'm already looking forward to OpCode 2021, coming back to Dubai, riding some camels and some Lamborghinis.
I don't know if I'm still going to do it next year. To be honest, I'm not sure if I'm still going to do the physical version again, because it's a lot of like logistic and stress and stuff.
So much work. Yeah.
And like doing the virtual stuff is pretty easy, but it's not the same. But at the same time, doing it like a physical event, you know, it's kind of tricky, you know, unless I would do it like in another country where it would like be fun, you know, like what we did in Kenya, you know. So it made sense to like do like the event in a new country because like the local community can benefit, you know.
Yeah. Well, keep me in mind. I'd love to, you know, come talk nerdy in person.
Yeah, sounds good. Okay, well, thanks again for coming, and yeah, talk to you soon.
All right, thanks, Matt. Aloha. Bye.
Aloha.